Alright, so here we have a question. Which of the following four graphs are bipartite? And we are required to give some sort of reasoning and justification as to why the graph we chose to be bipartite is indeed bipartite. And we need to give it either by giving a proper two coloring of the graph or by indicating an odd cycle of the graph. Now, a few questions you might have about this before answering would be the following. What makes a graph bipartite? A graph is considered bipartite if set of vertices, so given all of the vertices or the vertices of a graph, if we were to create a set of them, could be or can be property in that if you have a set with duplicate elements, so let's say a set has 1, 2, 3, and we can call this set A, the magnitude of A will be given by the number of unique items we have, right? So this will be 4, despite there being 5 elements, because in general, those duplicate elements are disregarded. However, when it comes to bipartite graph, if you can create a set of vertices, and these vertices will hold the information of its value and also the value that it connects to. So looking at this graph here, if you were to create a set of elements, each of these vertexes would have value of itself and every edge it connects to, right? So if we were to create this sort of set, we should be able to, if it is bipartite, divide this set in half such that both sets are disjoint, meaning that no two elements are in either set. In other words, and it'll become more clear what I mean by duplicates in terms of values and edges. And there's sort of two ways to prove this. So in terms of proof methods, you have one, the two coloring, and there's also the odd cycle system. And our question here asked us to use one of either. So I think, in general, the more logical and reasonable approach is the two coloring system, and I'll go into that now. Let's break up this word a bit more. The word bipartite is made up. The word bi and partite refers to the division of some element. So you can see so the word partite is sort of to part two things in and abroad. So bipartite itself means, can something be divided into two parts, which is where the bi part comes. So we ask ourselves, is our graph able to split into two parts? That's what our word means. And now with that, you might have a natural inclination to ask whether a tripartite graph exists. Given the definition of bipartite, that does exist. What we can do is generalize our definition such that every number is now instead an n, which means that our two coloring system would be n coloring system, and that number n will be made more clear to you later. So we should be able to make n disjoint sets or n unique sets given a n partite graph. Now, what is the two, or what we can call in a general sense, the n coloring? The n coloring method for those in computer science is similar to an algorithm what we call BFS, or in other words, red first. And now let me show you why this algorithm is similar to our n coloring method. Suppose that n is equal to 2. Okay, in terms of the bipartite system, when n is equal to 2, you have two options for your colorings. Okay, and I'm going to put quotations here. In terms of your coloring, these are two states that your elements can be in. We'll say red and blue, and we'll get some red and blue colors. Red and blue. All this means is that every element in our graph can be in either one of two states. It can be in a red state or blue state. So when it means coloring, it does not have to be coloring. This could have been instead 1 and 0, or I don't know, X or Y. It just has to indicate two unique states that a single element can be. And in terms of coloring, you are basically assigning the actual assignment of state. And this is the general algorithm. You'll see why this is similar to BFS. So let's say we have a beginning node. This first node, the same way it's chosen at random in BFS, you choose it at random when you're analyzing a graph, or possibly bipartite. So you first look at the first node and you check its neighbors, or what we call in graph theory adjacent. Two nodes are adjacent when they are linked by some edge. Let me delete these arrows because they could also signify an edge. Now if they are expressed by an edge, you must first label the first node that you're at by one of the two colors or two states, and then color the other two in the opposite. Now you've already searched this node. Now you must search either of the two nodes. We'll begin with the red node. Let's say that the red node has 3 neighbors. Okay, so there's 1, there's 2, there's 3. Now we require that we color every single one of these nodes in the opposite color of the node we're searching. Since we're searching the red node, these must be of blue nodes. Okay, so we've searched these two nodes. Now we need to search this node. Recall, if you don't know breadth first search or BFS, you must go layer by layer. Okay, so you don't go immediately all on the right side and then like this. You have to look layer by layer. So we first look at the topmost layer, then we look at the secondmost layer. So we search both of these nodes and then we search onward. Now let's say this second red node has also 3 nodes. Now we see here that we color everything in an opposite color. Now we've come to a node that both of our red nodes connect. Here we have no issues because both nodes attempt to color this node here. We'll solve A, B, C, D, E. They attempt to color this C node with the same color or the same opposite color, which is fine. We have no contradictions. So we've done all of our searches here, right? We've colored these properly. Now we color, let's say this blue node has only 1, but let's make an issue for us. We have this previous red node, this red 1 node, connects to this node as well. Going back into our algorithm, if we had searched this red node first, this means this red node had colored this blue node, this node in blue, right? Because we searched from top down or top level entity to bottom level entity. Now, suppose that this node has been colored, okay? So this node has already been colored. Now we're searching this node and its neighbors, okay? So let's give this node another neighbor. This node will naturally try to color this node red because it has no pre-assigned value. Okay, so this node is red. However, we have an issue here. This node has already been colored by another node in blue. Yet it is attempting to send a request to color this in red. Since we have two conflicting nodes, we know immediately that we have in discrete terms, a contradiction. So we have a contradiction here, right? So we are trying to attempt our node, to be both a blue and a red. Okay? Recall that this blue could have been a 2, and this could have been a 1, or any other 2 distinct sets, or distinct states. So, since this one node here is attempting to be 2 states at once, we have a contradiction, meaning that this entire graph is not a bipartite, and that is the 2 coloring system in a sort of vague sense. You continue to color nodes and its neighbors in opposite colors until you reach a contradiction. If you've colored the entire graph, then with no contradictions, then you have a bipartite graph. Now knowing this, let's go to our example here. So we'll begin with one randomly chosen node. We'll choose this one. We'll call this in red in our basic color, which you can choose. It could have been blue, but I'll choose red. Now we color neighboring nodes, and by nodes I mean these dots in the opposite color of the node you're searching on. So this is blue. Alright, we'll do a check mark to state that we've already checked. Now we'll move on to the next node. Oops, wait, no, sorry. This should have been blue. Okay, because these two are connected. Okay, now we will check this node. This node is connected to 2 other nodes, color in red, right? This is check. We have no contradictions yet. Now we have to check the other blue node, remember, because we go from top to bottom level. This B is coloring this node in red as well, which is fine, okay? There's no contradiction there, and it's connected to no other node besides its parent node, okay? So that's correct. Now we'll search this node here. This node is going to attempt to color this in blue, which is fine. Alright, and this node has no other connections, which means this is check. Now we check this node. This node is connected to only its parent and also its new neighbor. This new neighbor is of opposite color, which means this is check, and this is also check. In other words, this graph is indeed bipartite. Now let's go to the other graph. We'll choose this node as the 0 node, or the beginning node, the head node. We'll call this red, and this has 2 neighbors, or actually 3 neighbors. This will be blue, this will be blue. We've done the search on our first node. Let's move on to the second node. This node has only 2 neighbors, its parent and this other node. So we'll color this node red, and our parent node is of course the opposite color, so we can ignore that. We've searched this node. Now let's move to this node. This node has 2 neighbors, its parent and this neighbor. So we'll color this red. All right, now we've searched this. Now let's move to this node. This node here has two neighbors. Its parent, opposite color, and this. Despite this node only already being colored, because this attempted node here is of the opposite color, or the color that this node is trying to attempt to color with, there's no issues here. So this is checked. Now let's move to this node here. This node has two neighbors. Its parent, check. However, its other neighbor, R, is of the same color. This means we are sending a color request of blue and red simultaneously, and this causes an error, which means this is not bipartite. Now let's go to this one. This might take a long time. Okay, there's a lot of connections, so I'm not going to explicitly say each one, but follow along. You have red here, neighbor, 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 blue, 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 blue. Break this apart, check, move to here. This has neighbor, already, neighbor, neighbor. Already we have a contradiction here, in that this is a red request, and this is a blue request. So since these two nodes here, so we'll say node 1 here and node 2 here, connect to this node pi, we'll say, because they both connect to the same node and they send this opposite requests, this graph is not by. Now, of course, in a test, you would make that clear. We might label these nodes and color them figuratively. You'll say these nodes are colored like this, and then these two nodes, and you can label them. This is node pi, this is node beta, and this is node alpha. These cause a contradiction, and so on. Now this, again, I'll go quickly. Red, that's our head node. Then it sends two blue requests. Blue, blue, and also another one, blue. Now we're done searching this one. Now we check this one is checked. Connected to its head, its parent, and these two. So this will be red, this will be red. We have checked this. Now let's check this is connected to this one and its parent. All checks out. Now let's check this one. This one connected to its brother or neighbor and its other neighbor and its parent, all of opposite colors. So this is checked. Now let's check this one here. So this one is connected to this neighbor and this neighbor, both of opposite colors. No issues here. Now here, this is neighbors with all three of these, and they're all of opposite color. Ooh, yeah, all of opposite colors. Thus, there's no problems here, which means this graph is indeed bipartite. So circle, whoops, no. Okay, let's see what questions I have not answered for you. We've answered this, answered this, answered this. Now these more conceptual. What are these graphs representing? Well, graphs are versatile in that they can represent whatever they want. These nodes can represent whatever value they'd like, but the nuance comes in these edges that we call. These edges explicitly are defined such that any two nodes with an edge have an implicit, unless defined, relationship. Okay? Two nodes with a link or an edge, that we call, are related with some unknown relationship. Unless the problem defines for you, we don't know how they're related, they just are related. Okay, so graphs, just as you've seen, coordinate graphs with x and y, these relate data in kind of dual state points of x and y. These represent data through connections and value. Okay, how do we know if it's bipartite? Those two algorithms. Why should we know? Well, there's a bunch of problems in math, whether it be in computer science, in math, or in logic. Bipartite graphs, because they're versatile and can represent any data and any relationship, knowing how to know if they're bipartite can be a versatile skill. And what types of graphs are bipartite? Those that pass our N coloring method and also the odd cycle method. Coloring we've explained through this method explanation, and that should be all. Hopefully that helps.